14, meaning of scientific notation. So we're learning to understand the meaning of scientific notation, convert between scientific notation and standard notation, determine which number is larger or smaller in different notations. Okay, and so start off by saying, and this Lily just brought this up, has anyone ever seen this kind of number on your calculator? Okay, where you see a number and then a tiny little, it looks like an exponent of 45, but what that actually means is this huge number, 5.23 times 10 to the 45. It's so big that it can't fit on your calculator screen, so they write it like that for you. Okay, and same with this one, e negative 4, which some calculators show you, means times 10 to the negative 4. Okay, so that e negative 4, it could be an e 20, and then it would be times 10 to the 20th. Okay, so that's scientific notation. If your calculator tells you that, now you should be able to know, okay, that means I would take this number and move the decimal 1, 2, 3, 4 places, and that's what that number is that you see right here. It's 0.0008351. Okay? All right, so we're going to look at a little video, and I have a speaker. I have to make sure it's on. It looks like it's on, so this should be much better than it has been in the past. And we'll link here. Okay.
Nice shirts. Scientific notation is a concise way to express very large numbers, such as the circumference of the Earth in centimeters, or very small numbers such as the diameter of an atom. Scientific notation is written as a product of a number and a power of 10. Here's a number in decimal notation. That's a small number. Time for scientific notation. First, move the decimal over until there's just one non-zero digit to the left of the decimal point. The exponent indicates how many places the decimal point has moved to the right. This is the same as saying 5 4/10, divided by 10, 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 divided by 10. Woo! A more concise way to show you're dividing 5 4/10 by 10 8 times is to say you're multiplying 5 4/10 by 10 to the power of -8. That's using scientific notation. The method is similar for numbers that are really big. To change from standard form to scientific notation, just keep track of the decimal. For whole numbers, the decimal point is at the end of the number. Move the decimal point so there's only one non-zero digit to the left of the decimal. The exponent indicates how many places the decimal point has moved to the left. That's the same as saying 4 75 10,000ths times 10 times 10, and so on, for a total of 9 times. Multiplying by 10 9 times is represented by the exponent, positive 9. Why do we need this number to be between 1 and 10? To make it easier to understand, compare, and do arithmetic with extreme numbers. To understand this number, you have to count up all the places to see if it goes to the millions, billions, or higher. In scientific notation, we can understand that the value of the number is approximately 4 with 9 zeros after it. At a glance, these two numbers look like they're almost the same. To know for sure, you can count the digits, or you can use scientific notation. We can see that the number on the right will be bigger, since it is multiplied by 10 to the power of 10, whereas the number on the left is multiplied by 10 to the power of 9. Multiplying these numbers is a lot easier if you use scientific notation. First, you multiply the numbers separately. Let's round 4 75 thousandths and 3 95 hundredths to 4. The product of 4 times 4 is 16. Next, you multiply the powers. We know when powers are multiplied, exponents are added. Here we get 10 to the power of 19. The product of these two numbers is very close to 16 times 10 to the power of 19. As you can see, scientific notation makes it much easier to do math with extreme numbers.
Okay, so extreme numbers being very, very big or very, very small is where you'll use scientific notation most often. So in this first example here, we're going to write each number in scientific notation. And this one gives you a little prompt here. 9. So let's look here. So if I'm looking at this, I also like to know what number I'm dealing with. So that's 923,000. Okay. And now I'm going to do my decimal. So here's my decimal for a whole number. I'm moving it 1, 2, 3, 4, 5 places so that there's just one number in front of the decimal. So 9.23 times 10 to the 5. So I moved it 5 places to the left. Okay. This one. So that's every 3. So we kind of know what number we're dealing with there. So that's 120,300,000. So now I'm going to start my decimal off being here. And I'm going to move it so there's just one number in front of it. So I have to move it 1, 2, 3, 4, 5, 6, 7, 8 times. So it's going to be times 10 to the 8. 1.203 times 10 to the 8. All right, I want you to try the next 2. Who thinks they've got 430 million written in scientific notation? Yep.
4.3 times 10 to the power 8.
Yes. So you move the decimal from here. 1, 2, 3, 4, 5, 6, 7, 8. Awesome. Who thinks they've got 782,000 written in scientific notation? Molly.
7.82 times 10.
Perfect. All right, what about 1,021,000 written in scientific notation? Jacob.
1.031
Yes, good.
times 10 times 8.
Good. 1, 2, 3, 4, 5, 6. Perfect. Okay, let's look at this. 3 zeros and then 3 more zeros and then 3 more zeros. So that's 67 billion. Who has that written in scientific notation? Yep, perfect. 6.7 times 10 to the power of 10. All right. 0.03. Now we're writing a small number, so we're going to be using a negative exponent. Molly, did you know what it is? -2. So we would have had to move the decimal place 2 places to the right. So 3.0 times 10 to the -2. This one, we have to move it 1, 2, 3, 4, 5. Sorry. 5 places. So we have 6.042 times 10 to the -5. Does that make sense? Yeah. All right, try the next 2 on your own. Unpause this. What would it be? 0.00045. What would it be in scientific notation?
It would be, is it 45.0 times 10 to the power 3?
Okay, so you want to move the decimal 2, 3, 4 times.
4.5?
Yep. Times 10 to the.
Power 4.
That would make the number bigger. If you're multiplying by 10 to the 4th, you're making a big number. So you want to make a small number, so instead you're going to multiply by 10 to the -4. Okay, so knowing that, Paul, that's going to be any times 10 to the negative something. See if you can figure out what J would be. Close. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 to get the decimal so that there's just one number in front of the decimal. So the 3.42 times 10 to the negative 10. You get that, Paul? Okay. All right, you may go to the washroom. All right, and K and L. K and L?
I was looking up next.
Yeah, no.
That's confusing.
Okay, so Braden's already telling me it's going to be 6.23 times 10 to the something. Negative 11, good. Just remember when it's a really small number, it's times 10 to the negative something. When it's a really big number, it's times 10 to the positive something. Okay? And legit 1, 2, 3, 4, 5, 6 to the right. So I'm going to make a negative exponent. Okay, so remember these numbers are the same number, they're just expressed differently. Okay? Just expressed differently. This is a metric conversion chart. Okay, we'll see where we need to use it in these questions. But they basically show you that if you have like a femtogram, then it's very, very tiny, times 10 to the negative 15. If you had a picogram, times 10 to the negative 12, very, very, very tiny. Whereas if you get to a gigagram, that's times 10 to the 9, that's really, really big. Okay? Yep. All right, so standard notation and scientific notation. If a computer has 6.4 terabytes, so look at the tera and tera here. How many bytes does it have? Yep. Anyone know? Tera means you take the number and multiply by 10 to the 12. So 6.4 times 10 to the 12 bytes. That was easy because the number was already 6.4. Didn't have to use the decimal any more than that. Okay? So if a computer has 6.4 terabytes, it would have 6.4 times 10 to the 12 bytes. The wavelength of infrared light is 740 nanometers. So let's find nano. Use yellow this time. So nano is times 10 to the negative 9. So the first step for me is I could write this as 740 times 10 to the negative 9. But that's not really scientific notation, is it? For scientific notation, I have to write it as 7.4 times something. So how could I do that? Any ideas? What if I rewrite 740 using scientific notation? What would that be? 7.4 times 10 to the power of 2. 2. And then I multiply that. Good, Braden. Then I multiply that by 10 times 10 to the power of negative 9. And what happens when you multiply powers with the same base? You keep the base and add the exponents. 2 plus negative 9 is negative 7. Okay, did you see that thinking there? Okay, so we changed 740 graded to 7.4 times 10 squared. So we rewrote 740 in scientific notation. and then we still multiply by times 10 to the negative 9. And these have the same base. So when you multiply powers with the same base, you keep the base the same and you add the exponents to a negative 9. And that gives you negative 7. So that's going to be in their nanometers. So you need a little measurement inside that. Nanometers. Okay. A small amount of a sample has a mass of 3.2 times 10 to the negative 2 micrograms. Write this number in standard form this time, which means in decimal form. So we have to go up to micrograms. So micro is times 10 to the negative 6. So we've got 3.2 times 10 to the negative 2 times 10 to the negative 6. Grams, sorry, because it's asking me for grams. So again, I've got this idea where I'm going to keep the base the same and add the exponents. So negative 2 plus negative 6 is negative 8. But now I've got to write that in standard form, which means as a decimal. So I start off with 3.2, and then I'm going to move the decimal point to the left 8 places. 1, 2, 3, 4, 5, 6, 7, 8. So that's where my new decimal place goes. 0.00000000032 grams. So it should be a 0 decimal, and then 1, 2, 3, 4, 5, 6, 7 zeros, and then 32 grams. Sorry, that's in standard, scientific notation, but they want us to rewrite it in standard form. So we're going the other way this time. We're taking a number in scientific notation and we're writing it out in standard form. All right, and that's what we're going to do on the next one. So we want to write that number out in standard form. So when we see times 10 to the negative 6, your mind should be telling you it's a small number, it's a small number, it's a small number. So I know it's going to be 0.00 something. Okay? So this negative tells you small. So you're going to move your decimal 6 places. 1, 2, 3, 4, 5, 6. So 0.0000. 507.125 meters. Negative exponent indicates something small. A positive exponent indicates something big. Okay, so 2.245 times 10 to the 8. Positive exponent, big number. So I'm going to move the exponent 8 places to the right. So that's going to give me 5 zeros. And then if I wanted to say it out loud, I would put a little comma every 3. So it's 224,500,000 kilometers. Okay, we've got 2 more to try there, so see if you can write the first one for me. 0.0085 kilograms. Yes, everyone agree? Okay, 1, 2, 3, 4, so 0.000375 centimeters. Remember, the negative indicates small, small. If it was a positive exponent, it indicates you have a large. Okay, so Kaya is trying a tiebreaker question on Big Brother. The question is to estimate the product of 2.9 times 10 to the negative 4 product, so multiplied by 8.0125 times 10 to the power of 6. Whoever is closest without going over will win the tiebreaker. Kaya doesn't have a calculator, just a marker and a whiteboard. How could she come up with a winning answer? We kind of went through this a bit in the video. So what could I estimate this number as, 2.9? Instead of 2.9, could I make it 3? Is that close? And instead of 8.0125, could I round to 8? And that's all being multiplied together. So in the video they showed that you can multiply 3 and the 8, because everything's being multiplied. And you can multiply the powers of 10. So 3 times 8 is 24 times 10 to the power of, well, what do you do when you multiply powers with the same base? Keep the base and add the exponents. So negative 4 plus 6 is 2. So Kai is probably going to know what 24 times 10 squared is, right? 2,400. 24 times 100, 2,400. But she doesn't want to go over, so what might her guess be? What would be a good guess? Because maybe, like, the rounding might have made her go over a bit, so if she wants to be confident she didn't go over, what might she guess? A little less than 2,400? What do you think would be a good guess? 2,300? Now let's actually try it on our calculator and see what we get. See how good our guess is. So 2.9 times 10 to the power of negative 4. And ask your tutor how to put that in your calculator if you don't know. Times 8 times 10 to the power of 6. 2,320. Oh, good choice I made. I was close. If I'd done 2,350, I would have been over and out. Okay? So without a calculator, using rounding and powers, adding and subtracting, you can get there if you understand scientific notation. Okay? All right, so Kenneth is doing a calculation in chemistry. His calculator reads 5.2 e negative 10. What does this mean? So if he sees that on his calculator, what does that actually mean? In scientific notation first, what does that mean? 5.2 e negative 10. Yep. Yep. That's what it means, okay? So when he sees that on his calculator, he's going to write that down in his measurements, okay? And then, which number is larger? So we could write them in scientific notation to determine that. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So that's 1.1257 times 10 to the 10. And this one, 1, 2, 3, 4, 5, 6, 7, 8, 9. 9.5401 times 10 to the 9. Times 10 to the 10 is obviously bigger than times 10 to the 9. Okay? So that is bigger than that, so this number is bigger. So even though 9.5401 is bigger than 1.1257, this one's got another 0, which makes it bigger by 10, a factor of 10. Okay? This one's already written in scientific notation, so let's write this one also in scientific notation. So I got 8.8 times 10 to the negative 9. And it wants to know which one's bigger.
It's the other one.
This one's bigger, good. Because times 10 to the negative 7 is small, but times 10 to the negative 9 is even smaller. Okay? Even smaller.